Welcome to FMSP Online Revision. This session is for OCR D2 and the topic that we're going to be looking at is game theory. So let's have a look at what we need to be able to do with game theory. So we need to understand the idea of a zero-sum game and its representation by means of a payoff matrix. We need to be able to identify play-safe strategies and stable solutions. Reduce a matrix by using a dominance argument, and determine an optimal mix strategy for a game with no stable solution in two different ways. Firstly, by using a graphical method for 2 by n or n times 2 games, where n equals 1, 2 or 3, or alternatively by considering higher order games to linear programming problems that could be then solved using the simplex method. So just bear in mind, you won't actually be asked to perform the simplex method, but you might be asked to set up and show how it could be used. So what we're going to do is we're going to have a look at an exam question, which I think draws out just about all of these points. It is a very long question, as a number of these will be. So we've got a card game between two players consisting of several rounds. In each round the players choose a card from those in their hand. They then show these cards to the other and exchange tokens. The number of tokens that the second player gives to the first player depends on the colour of the player's card and the design on the second player's card. So the table shows this information. A negative entry means the first player gives tokens to the second. 0 means that no tokens are exchanged. Okay? So a number of different things we have to do. First of all, we have to explain how we know that it's a zero-sum game and describe what that means for the players playing the game. We've got to find the play-safe choice for each player, showing your working, to decide whether or not the game is stable or unstable, and to describe what that means for which and how the players are going to play the game. And the question then goes on and says the first player decides not to risk playing a blue card, so they'll just stick to red and yellow. Show that in this reduced game the circle strategy dominates the square strategy, and explain what this means for the second player when he plays the game. Then we're told that the first player uses random numbers to choose between the other two colours, where the probability of choosing red is p and yellow 1 minus p. We've got to write down an expression for the expected number of tokens that the first player is given in each round, and we've got to calculate the optimal value of p, showing your working. And then the question goes on and asks us to look at this idea of how we might use a simplex. So it says the entries in the row for blue are now all multiplied by -1. So for example, when a first player chooses blue and the second chooses a square, instead of the first player giving the second player 5 tokens, the second player now receives. In fact, the second player now gives the first player 5 tokens, so it's the other way around. The first player now uses random numbers to choose between the 3 colours, X, Y and Z. Denotes the probabilities of choosing red, yellow and blue. And the problem is then modelled in this linear programming. So this is our model. We've got to, in part 5, we've got to explain where the expression 5x plus y plus 8z comes from, this one. And then it says the simplex algorithm is used to solve the problem and the solution is such and such. Calculate the value of each of these expressions and hence write down the optimal value of m. So as I say, you're not actually using the simplex itself. So we'll break this question down into parts. So we're going to start by looking at these first two bits. So I've just sort of recopied the question for the first two parts. So let's see how we're going to actually have a go at that. So this is the table which shows us what's going on. So it says, explain how you know that the game is zero sum. And that is because whatever the first player gains, the second player loses. So notice that that's what we were told at the beginning, that if the first player gains something, then the second player will lose exactly those same number of tokens. So we could write whatever the first player gains, the second player loses. So overall the number of tokens will not change. So the total number of tokens will not change. So that's what we mean by zero-sum game. So basically that means, in terms of the players, it says describe what the zero-sum means for the way in which the players play the game. The one thing that we can say is that there is going to be no reason to cooperate with each other. So 1 mark for each of those 2 parts in part 1. And then it says find the play safe strategy for each player, showing your working. Explain how we know whether it's stable or unstable, and then describe what that would mean. So remember, in order to find the play safe strategy, we need to add on this extra column over here, and we find the row minimum. If player 1 chooses red, it's -1. If first player chooses yellow, then that's going to be -3. That's the row minimum. And if they choose blue, it's -5. And what we want to do is we want to take the maximum. So that is going to be the best thing, because we're going to lose the least here. So we maximize the row minimum. And similarly for the second player, we take the maximum. So the maximum there is 2, is 1 and is 3. And we then want to take the minimum, because that means that he's going to lose the least. So that's the first place. So that means that the game is not going to be stable. So the maximum of the row minimum and the minimum of the row max, for a game to be stable, those two have got to be equal, but in our case they are not equal, so the game is not stable. Right? So we want this play safe choice for each player. So this was red. So the best thing that the first player can do is choose red. So we better write that down. So the play safe strategy for player 1 is to play red. Play red. And the play safe strategy for player 2 is to choose the triangle. And I'll just put a little triangle in there because I don't seem to have enough room to write the word. And the next thing, describe what stable and unstable mean for the way in which the player plays the game. So in a stable game, playing the play safe strategy is always going to be the best strategy. So that is if we have a stable game. In our particular case, we don't have a stable game. Our game is unstable. So the play safe strategy cannot be best for both of them. So if we just write that down, so in a stable game, it's always best to play the play safe strategy. So playing safe is always best. But in an unstable game, it cannot be best for both. So play safe cannot be best for both. So we have 6 marks for that question. So we get 1 mark for getting our row minimums, our column maximums, and indicating the max and min. So 1 mark for each of these. So 1 mark for your max of your row min, 1 mark for your min of your column max. And that went together with this bit here, which was about the play safe strategy. So you got 1 mark here for saying that it was best for player 1 to play red and player 2 for the triangle. You got another mark then for showing that the game was not stable, because the max of the row min is not equal to the row min of the row max. And then you got a mark for each of these, explaining what a stable and an unstable game was. So 6 marks in total for that. So we'll move on to parts 3 and 4, and these sort of parts go together, so I've got them on the same slide. So part 3, first of all, if we come to that, it says the first player decides not to risk playing the blue card. So we're now going to cross this bit out. Show that in this reduced game, the circle strategy, which is here, dominates the square strategy, and explain what this means for the way in which the second player plays the game. So can we see that here 1 is less than 2 and -3 is less than -2, so it will always be better for the second player to choose the circle, because in this case he's going to lose 1 as opposed to losing 2, and here he's going to gain 3 as opposed to gaining 2. So that means we say that the circle dominates the square. So in the case of the red, 1 is less than, the circle is less, 1 is less than the square 2. And for the yellow, so I'm just making sure that so that's for the red. And for the yellow, -3 is less than -2. So that means that the circle dominates the square. So the second player would choose the circle, as he would always lose less. Or gain more. As he would lose less. So we need to write that down quite clearly. 2 marks, 1 mark for showing this in terms of the numbers, and 1 mark for explaining what that means to the second player. And then we'll have a look at part 4. it says the first player uses random numbers to choose between the other two colours. So let's just sort our table out here. We've already decided not to use blue, and now we know that the circle dominates the square, so we now have a 2 by 2 table. So the first player uses random numbers to choose between the other two colours, where the colour of choosing red is P and yellow is 1 minus P. So red is P, yellow is 1 minus P. So if the second player chooses the triangle, then that's going to be minus 1 times P plus 0 times 1 minus P. So that's just using the figures from here, the triangle, and that turns out to just be minus P. And assuming the second player chooses the circle, then it's going to be 1P plus negative 3 times 1 minus P, which is 4P minus 3. Now I've drawn these two lines here. So this is the line 4P minus 3, and this is the line minus P. The intersection of these points is what we want, because these are all the worst case scenarios, and what we're looking for is always the one which is at the top as high as possible, so the best worst case scenario. So that is when 4P minus 3 is equal to minus P. So 5P is equal to 3, and therefore P is equal to 3/5. So we've found the optimal value of P. So 3 marks for that. You got 1 mark for writing down these two expressions, 1 mark for finding P equals 3/5, and 1 mark for the diagram. So we'll move on then to the last part of the question, which, as I say, is the sort of simplex bit of it. So the entries for blue are multiplied by -1 and so forth. The first player now uses random numbers to choose between the 3 colours: X for red, Y for yellow, Z for blue, and so forth. It's modelled in this form, and we've got these 2 questions to ask. First of all, to explain where 5x plus y plus 8z comes from, and secondly, to work out the optimal value of m. So if we just have a look at that here, this is the table that we were given in the original question, but it then says we've got to multiply the entries in the row blue by -1. So that becomes 5, that becomes -1, and that becomes -3. So that means when the first player chooses blue and the second chooses a square, now the second player, first player gives 5 tokens, now it's the other way round. Okay, so the first player is going to gain 5 now. So we now have run using X, probability of red is X and yellow is Y and blue is Z. He uses random numbers to choose through these colours. Now before we can use the simplex, it's really important that to remember that you cannot use the simplex with negative numbers. So what we have to do is we have to add on to make this all the numbers positive. So we've got a -3 here, and that is our sort of largest negative number, so we're going to have to add a 3 onto the table. So we're going to add a 3 onto every element. So that becomes 524, that will become 130, and that will become 820. And notice then we're going to be maximising capital M equals m minus 3. So we do have to remember to take the 3 away again at the end. But the simplex needs positive entries in our table. So in part 5 it says, explain how the expression 5x plus y plus 8z is formed. Then that is formed when the second player chooses the square. So it's coming from here. So we have 5x plus 1 times y plus 8 times z. So for part 5 we're going to say something like, when the second player chooses the square, the first player expects to win 5x plus y plus 8z. 2 marks for that question. You got 1 mark for adding 3 on to each entry in your table to make all entries positive, and then you got 1 mark just for writing down that statement really. And the last part, part 6, says calculate the value of each of these expressions when x equals 0.6, y equals 0.4 and z equals 0, and hence write down the optimal value of m. So if we substitute into each, then we have 5x plus y plus 8z will be equal to 3.4. 2x plus 3y, so I'm just taking each of these values up here, each of these constraints. So 2x plus 3y plus 2z will be 2.4, and 4x, 4 times 0.6, again will also be 2.4. Now m has got to be less than or equal to all of these. So m therefore is going to have to be less than or equal to 2.4. So just bear in mind, as I say, that m has got to be less than or equal to all of these. That implies that m must be less than or equal to 2.4. But that, in turn, because m, capital M, is equal to little m minus 3, that means that m must be less than or equal to negative 0.6. And we want the maximum. And on the basis that we need to maximize, then that means that m will be equal to negative 0.6, because that's the largest value that it can be. So you had 3 marks for that particular part, 2 marks for substituting incorrectly into each of the constraints to get 3.4, 2.4 and 2.4, and then 1 mark for writing down the value of m, negative 0.6. Now that question has covered just about all the points that we looked at in the specifications. So it really does go through all that you need to be able to do on game theory. So it's just worth your while now just going through as many questions as you can and get lots of practice.